Hey everybody, welcome back to Computers and Computations. This week we'll be looking at our knowledge of arithmetic, and in particular how a neat little theorem called Tennenbaum's theorem has been used in the philosophical literature to try and perhaps give us some way of having knowledge of arithmetic. So, hope you enjoyed the talk. Okay, so without further ado, let's get into it. Good. So last week we looked at an application of the analyses of computation we've been looking at to ethical questions. And this week we're going to look at things from a slightly different angle. We're going to look at a very different application, more an epistemological question of how we gain knowledge of and reference to the structure of natural numbers. So this is more a question in the epistemology of mathematics rather than anything to do with ethics. So here's what I'll do. I'll talk a little bit in section 1 about different models of arithmetic. Then section 2 we'll talk about Tennenbaum's theorem. This is a theorem about recursivity of addition and multiplication on the standard model of arithmetic and how people have argued that that might allow us to isolate the standard model. And then in section 3 we'll consider an objection to this line of argument, namely that this response requires assuming a notion of finiteness, which is equivalent to just talking about the natural numbers. And I'll talk a little bit about how this is situated within the wider context, in particular just more theory style responses to model theoretic arguments. Before we get into the details, let's talk a little bit about the setup here. So for the purposes of this talk, we'll focus on the following two theories of arithmetic. The first is Peano arithmetic, first order Peano arithmetic, and this is formulated in first order logic, right? So we have just quantification into object position, and it has non-logical symbols, plus, times, naught, successor, less than. You can also formulate this with a 1 instead of the successor if you would rather. And then there are some fairly basic axioms. So we have, firstly, axioms for 0 and how it behaves with respect to the successor operation, axioms about the successor operation itself, the recursive definition of plus and multiplication, and then an axiom about the less than relation. And these 8 axioms together form what's called Robinson arithmetic, or Q. Okay. Now, the really important additional axiom to get you first order Peano arithmetic is the following induction scheme. Okay, so this says, look, if I've got some formula phi, right, with a bunch of free variables, but importantly, x is one of these possible free variables, then if it holds at 0, and for any object, if it holds, then it holds at the successor of that number, then it holds for everything. Okay, so the sort of motivation for this is thinking of the numbers like dominoes, right? So I have 0, and then I have 1, and then I have 2, and then I have 3, and then I have 4, right? And I show that phi holds of 0, but I also show that if phi holds for any particular number, then it's going to hold for the next number as well, right? And if I know that, then I know that phi doesn't just hold for 0, but because if it holds for any particular number, it holds for the successor, it's going to hold of phi 1, and then we're going to hold for phi 2, and so on. So it's the idea that we show that the first domino gets knocked over, and then we show that if any domino next gets knocked over, then the next domino gets knocked over, right? And so the motivation is that we thereby show it for all of the natural numbers. Good. A really significant point about the induction scheme is that it is exactly a scheme. So this is not one axiom. This is an axiom for every particular phi in the language of arithmetic of the required form. Okay, so Peano arithmetic first order is not finitely axiomatized. It has infinitely many axioms, in particular one for each instance of the induction scheme. Okay. Now this all changes when we move to second order Peano arithmetic. Okay. So second order Peano arithmetic is formulated in second order logic. And this is where, in addition to quantification into object position, right, we also allow quantification into predicate position, right? So we can say things like there is a property y such that y holds of x, for instance, whereas that's not permitted in first order logic. And in this context, we can formulate second order Peano arithmetic, and this has as axioms the 8 axioms of Q. But instead of the induction scheme, we've got an induction axiom where we say for all properties, if they hold of naught, and if they hold of a number, then they hold of the successor of that number, then that property holds for all numbers. Okay? So we can replace this scheme in the second order case with this axiom. Now this doesn't seem like a big difference, but once you come to look at the semantics for these different theories, you can get some quite significant differences with respect to the kind of structure they can pin down. And we'll talk about that in just a second. Good, so the worry we're going to look at comes partially from looking at different models of Peano arithmetic. And a standard fact from out the model theoretic literature is that Peano arithmetic actually has, the first order version, has many non-isomorphic models. Okay, what's an isomorphism? That's just a bijection between two structures, right? So this is a structure A, it has domain A, and it has a bunch of relations and functions and so forth. And structure B has domain B and a bunch of relations and functions and so forth. As long as they're in the same signature, you can talk about an isomorphism in the sense that of a bijection between the two that preserves truth, right? So I have my structure A over here, and I have my structure B over here. And an isomorphism is just a bijection between A and B, so it maps everything up one to one. But also when I look at any point A in A, if phi A holds over here, I know that phi of f of A holds in B. And vice versa, if I have some B here, and phi of B holds here, then I know over here that phi of f to the inverse of f of B holds over here. Okay, so it's one way of saying that A and B have the same structure. Okay, I can pair them up in such a way that all the truth stays the same in the relevant language, no matter whether I go back or forth. Okay, and what we know from some model theoretic results is that this first order theory of Peano arithmetic, the kind of standard theory of the natural numbers we'd like to have first order, has many non-isomorphic models, many models that differ on their structure. So here's one example, and to motivate it, we're going to look at the following theorem. This is the Löwenheim-Skolem theorem, and this states that if T is any countable first order theory, if T has at least one infinite model, then it has a model in every infinite cardinal. So we talked a bit about in earlier weeks how there are many different cardinal sizes, right? I can have Aleph naught. This is the cardinality of the natural numbers. And this is the sort of smallest infinite cardinal, but there are many infinite cardinals, right? I can have Aleph 1 and so on, this huge hierarchy. And in particular, for instance, the cardinality of the real numbers is greater than the cardinality of the natural numbers. We don't know exactly where it fits into this Aleph structure. That's a difficult question in and of itself. It can be shown that you can't prove it from our standard set theory. But setting that aside, we do know it's bigger than the natural numbers. So we do know that there's this huge hierarchy of cardinals. Now, what the Löwenheim-Skolem theorem shows you is that within this hierarchy, so long as my theory T has at least one model, let's say of size Aleph naught, it's going to have a model in every larger infinite cardinal. So this in particular implies that, you have countable models of Peano arithmetic. You'll have the standard model that we know and love, but there will also be lots of much bigger models in bigger cardinalities. So you have, for instance, a model of Peano arithmetic that's going to be the same size as the real numbers, for instance. There'll be some structure A that has the cardinality of the real numbers, but is such that it models Peano arithmetic, for instance. So an immediate question you might have is, how on earth can this be? I mean, I certainly was very confused by this as a beginning philosophy student. And the core point is that you can have models that have these so-called non-standard numbers, okay? So we're all familiar with what people often call the standard model of Peano arithmetic. This is just your friendly numbers, 0, 1, 2, 3, 4, 5, etc. And they have operations defined on the natural numbers, right? So we have the addition of 0 and 1, for instance. If we take the green to be the first input to the function and the red to be the second, 0 plus 1 is going to give you 1, right? 2 plus 3 is going to give you 5, so on. 2 times 2 gives you 4. And underneath it all, we've got the successor going along. And if we wanted to, we could talk about the less than relation that goes backwards like this, for instance, right? In addition to this friendly standard model, which is kind of what we normally think of the numbers as being, there are also non-standard models that satisfy Peano arithmetic. So we have the standard part, with the successor operation going off, but we also have these weird infinite natural numbers in inverted commas, what the model thinks are natural numbers, beyond all the natural numbers we normally think of, okay? Peano arithmetic itself can't fix the standard model. You can also have these odd non-standard model numbers off past the standard numbers you'd consider, and these the operations will also be defined on these non-standard natural numbers as well. So for instance, the successor operation still holds there because it's one of the axioms of Peano arithmetic that every natural number has a successor. Okay, now this is where we can bump up the cardinality very high, right, as in the Löwenheim-Skolem theorem. This part is always going to have cardinality Aleph naught, but we can perfectly well stick in kappa many natural numbers, or inverted, things that the model thinks are natural numbers for any particular kappa that we pick. Another place we see non-standard models crop up is with respect to the sentences satisfied by the relevant models. So in the last case we looked at, we were bumping up the cardinality of the model quite significantly. But you can also have models that are countable but satisfy different sentences from the standard model. So a neat example for seeing this is with respect to consistency sentences. Now we discussed consistency sentences a little bit earlier in the context of Gödel's incompleteness theorems. Okay. Now let's just recall a little bit of the details there. So if we let T be a consistent, recursively enumerable first-order extension of first-order Peano arithmetic, then we know by Gödel's second incompleteness theorem that T does not prove its own consistency sentence. Recalling that the consistency sentence says that it's not the case that there is some x such that x codes in T a proof of 0 equal 1, right? Now, since we're assuming that this particular T is consistent, we know that the real natural numbers, right, satisfy con T, right? So there is no proof of 0 equals 1 in T by assumption. And so on the natural numbers, when we look at codes of proofs, there's going to be no such proof, and so they're going to satisfy con T. But we also know that since T does not imply, proof theoretically speaking, con T, we know that T with con T, with the negation of con T added to it, is also consistent. Okay, if something doesn't, for first order theory, does not prove a sentence, I can add that sentence to the theory consistently. Okay, but now this critter here, this is a consistent theory. And so we know by the completeness theorem for first order logic, the theorem that every consistent theory has a model, that there is some model satisfying this theory, T plus neg con T, or not con T. Okay, but this is a really baffling thing, right? This model A both satisfies the theory in question, but also thinks that it's inconsistent. So what on earth is going on here? Well, here's what's going on. In this context, our structure A satisfying T plus not con T, so this is our structure A, and let's remember that it satisfies T plus not con T. A is very confused about what the natural numbers are. There are crazy things it thinks are natural numbers that are not real natural numbers. Now, remembering that natural numbers code up proofs, right? What's happening is that structure A is seeing some fake proofs. It's seeing some not real proofs in the non-standard part of A, right? So on the standard part of A, it's not the case that not con T appears here, but there's some wacky non-standard natural number that A thinks codes a proof of 0 equal 1 in T. This is not a real proof. This is some crazy infinitary object that A cannot distinguish from the regular natural numbers. It thinks it's a natural number, but it, according to A, codes a proof of 0 equal 1 in T, right? So this is what's going on here, and these things can perfectly well be countable, right? And they satisfy different sentences from the standard natural numbers. So what you have here is you have a particular model of arithmetic that is potentially countable, but also is very confused about what the sequences are, right? It's confused about what the proofs are, and for that reason it thinks that sentences are, or sorry, theories are inconsistent that are not actually inconsistent. Okay, so we have these two model theoretic kinds of observations that show that first order Peano arithmetic does not pin down the standard model of arithmetic for us. Now, there's a sort of skeptical position you might adopt on the basis of these two. So if it's not the case that our usual theory of arithmetic, Peano arithmetic, pins down the standard model for us, you might worry that actually thought and knowledge is not determinate about the standard model. Rather, we are only able to talk kind of schematically about different models of first order Peano arithmetic, and our thought and language doesn't suffice to pin down the standard model. Okay, so there's kind of we have this skeptical worry, and with this skeptical worry we have kind of two questions or challenges. And the first is that, well, is the skeptical worry true? Do we gain knowledge of or reference to the standard model of the natural numbers, or are there rather just schematic talk about many models of first-order Peano arithmetic? And indeed, if we are able to gain knowledge of reference to the standard model of natural numbers, how do we do so, or perhaps how can we do so? Now, there's an immediately kind of bad answer we could give to this skeptical challenge, and that is that we gain access via using second-order Peano arithmetic. We might point to the following theorem here, and that's using the semantics for second-order logic, where the range of the second-order variables or quantifiers is every subclass of the domain, right? All models of second-order Peano arithmetic are isomorphic. So as long as we have access to all the subclasses of the domain, I can show you that if that thing satisfies second-order Peano arithmetic, it's isomorphic to any other thing satisfying second-order Peano arithmetic with the full subclass interpretation. Okay, so in the context of second-order Peano arithmetic, as long as we have a very strong kind of semantics in the background, we do get characterization up to isomorphism. Okay, but there's a kind of, although this is a perfectly good result from model theory, it's kind of unsatisfying in the context of responding to the challenge of the skeptic. Because in this case, I have to use the idea of an arbitrary subclass of natural numbers in making it precise what the natural numbers are. So if I'm already worried about what my access to the natural numbers might be, it's no good for me to assume access to arbitrary, the notion of arbitrary subclass of natural numbers. This issue is made even more acute when you look into the model theory a bit, and you can find these semantics for second-order logic. These are called Henkin semantics, for which things like the Löwenheim-Skolem theorem does hold. And in fact, in this context, second-order theories are equivalent to two-sorted first-order theories in the kind of properties they have for Henkin semantics. So they have, if you know some model theory, they have things like compactness properties, and they have, as I said, the Löwenheim-Skolem results hold. So the point is that this requirement that I have the full notion of arbitrary subclass in the background is important for getting this, and indeed essential for getting this characterization of the natural numbers up to isomorphism within second-order Peano arithmetic. But this kind of observation, this kind of response does raise the following possibility or suggestion, and that is, look, is there some sort of result that we can appeal to from model theory or our understanding of natural numbers that firstly allows us to differentiate the standard model of arithmetic from the non-standard ones, but does not presuppose access to the standard model in doing so, or in the case of PA2, something, it seems, even stronger than the standard model, the idea of arbitrary subclass of natural numbers. And this is exactly where results about computability are going to come in. The idea is going to be that, look, the non-standard models do not obey principles we think the natural numbers should have with respect to the computability of the multiplication and addition operation. So one suggestion that has been made several places in the literature is the idea that the following theorem, called Tennenbaum's theorem, does the job for us. So Tennenbaum's theorem is the following. So it says that if some structure A, which has domain A, and it has an interpretation of 0, successor, plus, times, and less than, is a countable model of piano arithmetic, and plus and times are recursive, i.e. computable functions, then A is in fact isomorphic to the standard model of arithmetic. So the only times where we can have plus and times to be computable are exactly in the case in which that A is isomorphic to the standard model of arithmetic. Okay, with this in hand, we can run the following kind of philosophical argument. We might say that, look, when we learn arithmetic, we learn how to compute the operations of addition and multiplication, right? This is the kind of thing we do at school. We learn how addition and multiplication behave, and as part of this, we learn the particular recursive rules for addition and multiplication, and we kind of see that they're going to be computable, right? And in doing this, we see that they're recursive. We see that they're computable. We have the rules for how they should be applied, and we can see that whenever we get two numbers, there's a way of computing their sum or their product, right? Now, if A is uncountable, this is our possible structure of the natural numbers, the question of whether plus and times are recursive does not arise. You can't have computable functions if the domain in question is uncountable. It's just too many things. You'll never get to the uncountable entities. Okay, but if our model is countable, then the only model we have with plus and times recursive by Tennenbaum's theorem is the standard model. So the argument goes, look, we understand that the operations plus and times must be computable, and this perhaps gives us access to the standard model of arithmetic. Knowing that plus and times are computable, we then know that that our thought and language refers only to the standard model of arithmetic when we want it to, because for the other models, they have non-recursive addition and multiplication operations. Now, on the one hand, I think this kind of argument is very tempting, and I think Tennenbaum's theorem definitely has philosophical implications. But I also think it should be unconvincing to the model theoretic skeptic. And this is dealt with very nicely in a paper by Button and Smith called The Philosophical Significance of Tennenbaum's Theorem. And the key problem is this earlier desideratum that we looked at, that you should not presuppose the resources you are trying to fix in showing access. So in particular, we can't presuppose access to the natural numbers in trying to show that we have access to the natural numbers using some model theoretic results if we want to answer the skeptic, right? And this is in particular only for answering this kind of very strong model theoretic or natural number skeptic. Okay, I'll say a little bit about what the place of Tennenbaum's theorem might be if you're not a skeptic in the conclusions. And the core problem is that in order to say what a computable or recursive function is, you have to talk about a computer halting or some equivalent in terms of recursiveness given an input after a finite number of steps, right? I have to appeal to the notion of finiteness in characterizing what it is for a particular function to be computable or recursive. We can see how deeply this kind of runs. Saying what it is to be finite really does require access to the natural numbers. And to see this, let's introduce the following quantifier into our language. Let's have there exists thin to be a quantifier expressing the claim that there are finitely many, right? Now, assume we give this quantifier its sort of standard interpretation. You could then pin down the natural numbers with the following sentence, right? You say that for any x, if x is not equal to 0, then x has exactly finitely many predecessors. So it has finitely many predecessors, right? So the thought is here, I have some model of arithmetic, and for all I know, it's non-standard. But if I say that for any particular member of this structure, there's only finitely many predecessors, then I'll be able to distinguish it from the non-standard models, because the non-standard models have all these wacky non-standard numbers out here, which have infinitely many predecessors, okay? In particular, the whole standard part is going to, each member of the standard part is going to be a predecessor of this, of some n star in a wacky non-standard model. So if you introduce any notion of finiteness and say it's determinately understood, it's going to allow you to pin down the standard model of arithmetic anyway, and in some sense pinning down finiteness is just assuming access to this idea of the standard natural numbers. And I think this is more vivid when we consider that, for instance, any non-standard model of PA will think that it has plus and times recursive, right? So our particular wacky model here, right, it thinks that the operation of plus and times is recursive, even though it's not. Why is this the case? Well, it's very similar to cases to the Gödelian case. It's very confused about what numbers are really finite, right? So it might think that this, n star plus some other n star, let's call this n star 0 and this n star 1. It thinks that this operation here is recursive, but it only does that because it can do, large infinitary kind of computations. It's confused about what is really a finite computation, right? It's only when we step outside the model using our understanding of natural numbers that we see that A was confused about what the recursive functions are. Okay, so the only way we can use Tennenbaum's theorem to pin down the standard model is if we assume access to the natural numbers in characterizing the notion of computation, and this isn't going to convince the skeptic about the natural numbers, precisely because they're not going to think that we have, or they're worried about our access to the notion of finiteness anyway. So this is an interesting kind of argument because it's a species of what's known as a just more theory argument. Okay, so these are arguments. They appear a lot in philosophy of language, but in the philosophy of mind, where we have some kind of skeptical worry about reference or indeterminacy, and we appeal to more theoretical resources in trying to refute the skeptic. So one example, for instance, is if you're worried about the reference of our properties in general, you might move to talking about natural properties. There are only properties that carve at the joints. Those are the only legitimate properties. Something along those lines. The problem is with these kinds of responses in general across philosophy is that when you appeal to just more theory, you open this extra theory you've appealed to up to reinterpretation too, right? So this is exactly what happened in this context. We appealed to notion of computation, but that in turn is open to reinterpretation if you don't, or you aren't sure that we have standard access to the natural numbers. Similarly, if you think there are natural properties, you might think that the idea of a natural property is up for reinterpretation. This is dealt with in a lot of detail in Tim Button and Sean Walsh's book, Philosophy and Model Theory, if people want to look at that more. But the core point here is just that if you are going to appeal to a just more theory type argument in trying to respond to a skeptic, you had better be sure that that more theory you appeal to isn't something that the skeptic can reinterpret. It has to be somehow weaker in flavor than the resources you are trying to characterize. And I'm not aware of any context in which this kind of argument has really been carried out successfully. And in my opinion, in the context of computation, it's pretty clear that this problem of appealing to finiteness is going to be very, very hard to get rid of if you want to use Tennenbaum's theorem or something similar. Okay, so just to sum up and maybe point towards some philosophically interesting ways we might take future study of Tennenbaum's theorem. So I think as a response to the skeptic, Tennenbaum's theorem is unconvincing. And this is not my point. As I mentioned, this has been pointed out variously in the literature. However, I do think Tennenbaum's theorem is really quite philosophically interesting. Okay, aside from skeptical worries, let's assume that we do have a decent access to the natural numbers. I think that's very plausible. And what it shows is that any perturbation in the notion of finiteness from our standard meaning, so any move to some sort of non-standard model, is going to ripple out into the really most basic computable functions. So there's no kind of, what it shows you is there's no kind of standard model in which non-standard model which you can move to, in which nonetheless basic operations like multiplication and times remain recursive. Any non-standardness is going to infect even the very most basic arithmetical operations. Okay, and I think this feeds back, and this has been pointed out by Walter Dean, into considerations about feasibility, for instance. So both plus and times have very feasible algorithms. They're both in p-time. In fact, you can do them a bit faster. So what Tennenbaum's theorem is going to tell you is that these very easily computable functions, highly feasibly computable functions, if you move to a non-standard model, they're going to become non-recursive, even though they're like easily computable on the standard model. So Tennenbaum's theorem's telling you something very important about the difference between the standard model of arithmetic and non-standard models. It's telling you that when you move to a non-standard model, really the very most basic aspects of arithmetic are kind of going haywire. So even if I think it's not good as a response to the skeptic, I think there's still philosophical interest to be had in looking at it and thinking about what this might tell us about the space of models of arithmetic we're working with. And there's definitely a bunch of interesting philosophical questions that one can ask about further significance of Tennenbaum's theorem. Okay, thanks very much for listening.